Imagine a 2-ton vehicle traveling at highway speeds down a pitch-black, unlit rural road. Its headlights illuminate only a fraction of the asphalt, leaving the computer vision system effectively blind to anything just past the beam. This chart shows the effectiveness of autonomous emergency braking, or AEB, in preventing nighttime pedestrian collisions. In 2019, the American Automobile Association tested these systems in total darkness. The avoidance rate was absolute zero. Every single test resulted in a collision. By 2025, that nighttime avoidance rate shoots to 60. Statistical distribution of driving scenarios. The massive peak on the left represents routine driving, clear weather, and predictable traffic. But safety is determined by the endless flat tail on the right. This long tail represents highly specific edge cases that occur infrequently but carry a severe risk of fatality. Out here in the extreme right of the tail, you find scenarios like a pedestrian who has fallen in a crosswalk, or a child wearing an oddly shaped Halloween costume. Because these events happen so rarely in the physical world, driving millions of miles on a sunny highway will almost never capture them. Passive observation cannot collect enough rare examples to prove an AI system is statistically safe. A perception model navigating perfectly on a clear day can be instantly swallowed by blinding dense white fog. This is an out-of-distribution, or OOD, event. A model trained exclusively on clear conditions lacks the mathematical weights to process the noise and distortion of heavy fog. OOD inputs trigger a specific failure mode, overconfidence. The system encounters the fog, misidentifies a truck as a patch of open sky, and accelerates into the collision. To address this vulnerability, the automotive industry published a regulatory standard in late 2024 called ISO PAS 8800. It defines the safety and quality management lifecycle for AI systems in road vehicles. ISO 8800 classifies datasets as legally bound safety artifacts. This requires strict version control and complete traceability, replacing unmanaged pools of raw data. If a physical dataset exhibits gaps in representing intended operating conditions, the standard mandates those gaps be filled. Engineers must use algorithms to augment existing data or synthesize completely new virtual data to cover the missing edge cases. Under these regulations, data serves as an engineering specification that must be designed to prove statistical safety, rather than a resource to be passively collected. Data augmentation maximizes the utility of the physical miles a company has already driven by mathematically mutating the existing images. In photometric perturbation, the computer treats an image as a number matrix. An algorithm multiplies a grid of Gaussian noise against the base grid. This injects patterns of dark environments, water droplets, or motion blur, simulating a storm mathematically without physical rain. Researchers also use frequency pixel connect for domain adaptation. By merging the amplitude spectrums of a clear day image and a foggy target image, the algorithm preserves the semantic structure, keeping the shape of the pedestrian intact while expanding the environmental diversity the model can process. In adversarial adaptive data augmentation, the system actively attacks its own perception model, injecting specific perturbations into the data stream precisely where the AI is weakest to force adaptation. These mathematical mutations act as a strict regularization mechanism. They stop the AI from memorizing fragile images of a sunny street, forcing it instead to learn the underlying, robust features of the objects it needs to avoid. When modifying existing images is insufficient, engineers use simulation engines to build reality from scratch, safely creating scenarios that are ethically impossible to collect. You cannot ask a human to lie down in front of a moving vehicle on a dark road just to test if the camera recognizes a fallen pedestrian. To capture these scenarios, developers use generative engines like world models. A world model is an AI system that learns the physical rules of an environment, allowing it to synthesize realistic 3D scenarios based on a text prompt or a map. Using platforms like Carla or NVIDIA Isaac Sim, an engineer can digitally sculpt a high-fidelity model of a fallen pedestrian, placing it exactly in the path of a virtual sensor array. The simulator executes domain randomization. It takes a single 3D model, cycles through variables, changing the street lighting, adding heavy snow, and swapping textures frame by frame. By generating synthetic data, developers mass-produce thousands of variations of the fatal edge cases hidden in the long tail, bypassing the limitations of the physical world. Physical data carries a massive economic bottleneck: human labeling. Drawing bounding boxes around objects in millions of video frames is expensive and prone to the subjective fatigue of human annotators. Synthetic data automatically extracts flawless ground truth labels. The rendering pipeline outputs a z-buffer for precise depth coordinates, calculates optical flow to track exact movement velocities, and executes instant segmentation to assign pixel-perfect boundaries to every object with zero margin of error. Simulation-based generation produces targeted test scenarios roughly 2.5 times faster than manual curation, with a 0% human error rate. The rendering pipeline eliminates the economic bottleneck and manual labeling. It turns the simulator into a data flywheel, churning out structured information that human annotators simply cannot see. Synthetic data introduces a critical vulnerability. If an AI model overfits to the artificial quirks of a virtual world, it will fail when deployed on a real road. Engineers separate this into two threats. The first is the reality gap, where the simulated physics or sensor noise fail to match reality. The second is the performance gap, where algorithms that run perfectly on simulation servers experience latency on the vehicle's hardware. ISO 8800 requires proving simulation validity using the Pearson correlation coefficient. One bell curve represents the virtual vehicle's behavior, the other the real vehicle's. By fine-tuning synthetic models with real-world data, engineers execute domain adaptation, aligning the domains until the performance curves perfectly overlap. Synthetic data only counts as a valid safety artifact if rigorous statistical correlation proves that the virtual tests mirror the chaos of the physical world. A vehicle can now internally simulate dozens of possible futures in real time, branching out from its current position to find the safest path. This hybrid ecosystem operates as a continuous loop, collecting real data, performing gap analysis, synthetically generating edge cases, and validating results. Integrating large language models instantly generates complex 3D environments from text prompts, accelerating the entire flywheel. Targeted synthetic generation, not the accumulation of more physical miles, delivered the 60% jump in nighttime success. Engineers use this pipeline to systematically attack the perception model's known blind spots. Autonomous safety now demands the mastery of virtual creation. By engineering the unpredictable in simulation, developers ensure the machine is prepared to protect human lives in reality.